Okay, so I pulled up another organic structure. I think you say its name remdesivir, and it is an Ebola drug that they're trying to fast track through trials to see if it can successfully fight COVID-19. And so I pulled up a picture of the drug over on the left, and then I pulled up a picture of adenosine. So, do you guys see any similarities between? Well, and first of all, what's adenosine? Do you guys remember?
Is that the was it a flu drug?
Nope, nope. That's Tamiflu.
No.
That's Tamiflu. Hey, Tamiflu and
Uh,
remdesivir have similar structures, and they fight in
mhm.
similar mechanisms. But adenosine is. Do you guys remember? A You probably remember ACGT, right? From biology, maybe. Those are the DNA building blocks.
Oh yeah.
Okay, well, hey, ACGU or AGCU, that's adenine or adenosine, guanine, cytosine, and uracil. And those are the building blocks of RNA. So a bunch of sequences, like if you have like AACGU, AAAGCGCAAA, that's what makes RNA, and that's what codes for simple structures like viruses, and some bacteria will have just RNA in them. We actually take our DNA and turn it into RNA before it builds proteins, so we have an extra step in human cells and in animal cells. But viruses just have RNA, and so it turns out that COVID-19, they've gene sequenced it, and they found that it's heavy in A's. So it's heavy in adenosine, and since it's heavy in adenosine, they thought if they found something that structurally looks like it, then when the virus is trying to replicate itself, instead of using actual adenosine, it gets drug molecules stuck in it. So do you guys see the part of the drug that looks like adenosine?
Um.
Does
Okay.
this make sense? That those are I pretty much
Yeah.
they're not quite the same. Do you guys see how, like, I think the nitrogens are a little different, but
Yeah, they kind of look.
they're very very close, and it's got this weird little triple bond, but the structure and shape is very close. Well, they're hopeful that these basically replace all the A's with R's, and then there's a little enzyme that comes along here. I'll do it in blue, and it basically attaches itself to an RNA chain, and it moves along, and instead of passing along like AACGU, when this little enzyme protein gets to an R, because this R has some extra funky stuff hanging off the end of it, like all the R's have extra funky stuff hanging off the end, like it's this piece. That's like, I'd call it a dangler. Well, basically, when the little enzyme that's crawling along that RNA strand gets to an R, it has trouble. It has trouble, and it gets confused and doesn't know how to proceed. So it basically stops the replication. So that's what they're hopeful
So it
for.
stops COVID-19 from producing more in the body.
Correct. It exactly like COVID-19. All it does is it pops into your cell, and then there's ribosomal RNAs that basically crawl along RNA strands and replicate it. And that little RNA, the little ribosomal RNA, cannot crawl along if there's these chains hanging off of the RNA strand. And so
Okay.
by adding these extra chains in there, they're hopeful that it won't be able to replicate, and it all has to do with molecular structure. So they found something that a drug, or they produced a drug that's very similar in structure, but not exactly the same, and it has extra stuff in it. And this is how all drugs work. And this is called probably a amino acid therapy drug, and it's trying to replace amino acids to stop transcription from happening. So okay, so there's your biochemistry lesson of the day.
That's all.
I'm gonna go to number 4. So number 4, 5, and 6 are shorter questions. So I'm hopeful that we can get through at least 2 of them. So here is number 4, and sorry if it's small. I'll try and read it. This question is more of a theory question. It says a student's experimenting with carbon dioxide gas. Originally, the gas is in a rigid container at 299 Kelvin and 0.7 atmospheres. Oh, Keaton, we can't hear you. 0.7 atmospheres. It says the student increases the temperature to 425. So A, and maybe instead of me writing it, I don't know if somebody wants to try it. Can someone describe the effect of raising the temperature? How would it affect the motion?
Yeah, I said if you raise the temperature, the CO2 molecules will begin to move faster and the pressure would increase.
There you go. So they move faster. Yeah, what else are there?
Kinetic energy of the particles increases, like
Yep.
hitting the sides of the container more, increasing the pressure.
Yep. And you're jumping ahead to B. So calculate, or to C, sorry. Calculate the pressure in B. It says, what's the CO2 at 425? So B, PV equals nRT. And here's the weird thing. They don't give you anything about the volume, right?
Yeah.
So,
Well,
again, remember.
You just group the constants,
Okay,
right?
Arthur, you're on it. Yep. So R is constant, the number of moles is constant, and the volume, the container, is constant. So the only things that are changing are P and T. So I'm going to move the T over here and the V over here. So really it's like P over T equals NR over V. And this is all a constant. So you can do this. P1 over T1 equals P2 over T2.
Okay.
So yes, if you're not given everything, because there's, let's see, R is always a constant. So there's 1, 2, so 1, 2, 3, 4. There's 4 variables in the gas law. If you're not given all of them, then something has to be held constant. So you need 3 out of the 4, or you need to know that at least one of them is held constant. So P1 was 0.7 atmospheres, and the original temperature was 299 equals P2 was 425 over, oops, no, that's T2. P2 over 425, okay. So you multiply both sides by 425, and you end up getting P2 was 0.99. And I'm just, to make this go faster, I just printed off the answer so I don't have to calculate. But so that algebra is not bad. Okay, C, Arthur already mentioned, says in terms of kinetic molecular theory, briefly explain why the pressure of the container changes as you heat it. So Arthur said higher KE, higher kinetic energy means faster particles, which means more collisions with walls, which means higher pressure. There you go. That's correct. Okay, and then another review. What's the only thing that'll change the kinetic energy of a gas? Like
pressure?
Not pressure. Pressure will increase the number of collisions, but it doesn't change the kinetic energy.
Keaton asked a question. That's if it's in an open container, but since it's in a fixed volume, the volume can't increase, so the pressure does.
Yep, correct. And yeah, so what's the only way to increase the kinetic energy of a gas?
Change the temperature?
Yep, you got to heat it up. So this is the question that they will ask. They'll put something like helium, which is light, versus neon, and they'll say that this is at 425 Kelvin and that this is at 425 Kelvin, and they're going to try and trick you. They're going to say which one has a higher kinetic energy, and your answer would be which one has a higher kinetic energy?
like I can't remember. It's either neon because it has more mass, or helium, or neither. Because they're the same.
They have the same kinetic energy because they're at the
hel-
same temperature. But what's different about the helium?
It is moving
The
faster.
helium is moving faster because kinetic energy is 1/2 mass times velocity squared. So if, let's say, you have the helium 1/2 mv squared on this side and 1/2 mv squared on this side, and this is the helium mass, whoops, and this is the neon mass, okay, and those two sides are equal, and neon weighs, I don't know how much it weighs, 10 or 20 or something, 20, and helium's 2. Okay, then the velocity for helium has to be much higher, right? If this mass is smaller, then the velocity here has to be bigger. Make sense?
Yeah.
Now, do you think it's proportional? Like if this one is 10 times bigger, if neon is 10 times heavier, sorry, and it's not 10 times heavier. I think helium 4.
No, I think
Helium has a mass of 4.
Okay.
And neon has a mass of like 20-ish. Okay, so if you're looking at that, it's like 5 times heavier. Do you think that means helium moves 5 times faster? Why? Yes or no, and why or why not?
Okay, it's mass velocity squared.
So
wait, are you saying if helium is
if helium is 5 times lighter, do you think it moves 5 times faster?
Yes.
Not quite, because I want you guys to see that this is messing it up.
Okay.
Okay, so
the squares.
So here, let's try this. 1/2 times 4 times V helium squared equals 1/2 times 20 times V neon squared. Okay, what cancels right away?
The 1/2.
The 1/2s. Okay, and then if I say move the 4 over to the other side, I get V helium squared. Oh, and I'm gonna move the neon velocity over to the other side, equals 20 over 4. So I just rearrange things. And then if I wanted to compare the ratio of the velocities, so I get V helium over V neon equals the square root of 5. And you guys know what the square root of 5 is? Like 2 times 2 is 4. 2 times 2 is 4. 3 times 3 is 9. So it's got to be kind of close to 2, right?
Something.
It's like, well, 3 times 3 is 9, so it's going to be at 2 point something. 2.2, 2.3. Okay, and that's basically saying that the velocity of the helium is about 2.3 times faster. So now remember, it was 5 times lighter, right? 4 compared to 20. But because of the square root, it's not like it's 5 times faster. It's only 2.5 times or 2.3 times faster. Okay.
Okay, that makes sense.
Yeah, but the big thing, you guys, because there will. Oh, and I can't say this. Had there been multiple choice, they absolutely always throw in the question where they try and trick you, because this is fundamental. Everything at 425 Kelvin, everything has the same kinetic energy. The only difference is some things are lighter, so they move faster, but they all have the same kinetic energy. It turns out temperature, like when we say it's supposed to be 70 degrees outside today, right? When we say it's 70 degrees Fahrenheit, this is actually measuring kinetic energy.
Okay.
That is a kinetic energy. So everything that's at 70 degrees Fahrenheit has the same kinetic energy. Okay? So we just call it temperature, but we're really measuring energy. Okay, next one. D. It says the student measures the actual pressure of, let me scroll up. Measures the actual pressure of the carbon dioxide in the container at 425 and observes that it's less than the pressure predicted. Explain this phenomena. So
it's because atoms take up space.
Correct. That's one reason. So if you've got CO2, okay, and they're trying to hit the walls, right? A perfect ideal gas, the only thing that's happening is they're bouncing off each other and they're bouncing off the walls, right?
Mhm.
Well, why is, this is an important one, why is CO2, like say the one on the left, attracted to the one on the right?
Intermolecular forces.
Intermolecular force, yep, specifically London
London
dispersion force, because CO2 is what?
Non-polar.
Non-polar. So you have London dispersion forces attract because electrons in the non-polar CO2. London dispersion attract because can shift. There you go. Okay, so you've got electron clouds that shift, and then hi Keaton again. Hey, it works now.
There we go.
It
I know
works.
how to hit it each time now.
Yes. Also,
Okay,
thank
so
you, Keaton, for pointing out that neon is 20.18.
I have a PRN cable as a desktop background. All right. I was trying to say it earlier, but all the atomic weights. Oh.
Hi. I think this question will not be on the test, because I think you guys, had I not been writing and talking, you guys could have gone through that one in 5 minutes. And they told us that they told everybody it's going to be one question that takes 25 minutes, and then a second question that takes 15. So
in the writing portion.
Yeah, there's only writing. There's no multiple choice.
Okay.
So it's a 25-minute question. Yeah, like the questions 1, 2, and 3 on this year's or 2019's test were very long. I would assume that the first question you do will be the same length as one of those. So we did like number 3 yesterday. It was exceedingly long. Like I didn't even do the whole thing, and it took us 30 minutes. So I would imagine you're gonna have one that size, and then you're gonna have
Wait,
one.
so
Yeah. Go ahead.
the whole test is problems I have to solve out.
It's 45 minutes. Problems you have to solve. Yep. 2 questions. That's 2 questions. That's it.
Okay.
Okay. Let's go on to E.
You just look at the paper. The first question is, what is your name?
Yeah.
What is your quest? What is the airspeed velocity of an unleaded
what if they
ball?
just prank us and just like put on there, what score do you want? And it's like that's the only question on the test.
You can dream. You can dream. They've spent a lot of money making sure that this happens. They said that in the last 3 weeks, they've dipped into their reserve because they're not generating any more revenue through, I don't know what they generate revenue through. They're a nonprofit, and they're spending extra money, more than they had budgeted, so that they can transition everything to online. So
wow.
Yeah, he was adamant that this is going to happen.
Will the test this year be worth the same amount of credit?
Yeah, he said that they have 125 colleges who've agreed to still accept the credit as normal.
That's awesome.
Yeah.
I should probably check and see if he accepts that.
Yeah. Okay, so let's look at 5. So this is PES. Stands for photoelectron spectroscopy. Basically, this was the soccer ball. Yeah, this was the soccer ball in a ditch. Okay, so whenever you see something like this, and I kind of doubt that they'll throw a question like this on. They might, but it would be with only 2 questions. This is not the most important. I would say that there's going to be an ideal gas law. There's going to be something involving enthalpy, and there's going to be something involving intermolecular forces. So this one would be a stretch. Maybe they throw something in, but I'm not certain. So, okay, when you see this, first thing you got to do is identify where the nucleus is in this picture. So, because sometimes they're drawn reverse, where is the nucleus? Is it on the left side of the x-axis or the right side? Yep.
Yeah.
Oops, I should put nucleus. Why?
Because
it takes the most energy.
Correct. Yeah. These 2 electrons are held the strongest because they have no electrons between them and the nucleus. So it's a pure 2 electrons with some positive nucleus in the middle, and there's no electrons in the way. other electrons in the way. So that is, and the distance is the closest. So those ones are held the tightest. So that's the biggest number. So based on the spectrum, right, the ground state electron configuration, we go 1s2. That one only holds 2, right?
Yeah.
And then these are which orbitals?
2s2,
2s2 and 2p6. Yep. And then we've got
3s2, 3p6.
Okay. And then last one.
4s2.
Yep. Okay.
So I have a question.
Yeah.
Would writing it shorthand also work?
Mm-hmm.
So if I were to say like I put just I think that's what is that? Argon plus 2 more. Yep.
Yeah, argon 4s2. Yep, that's fine.
Okay.
Okay.
Identify the element, so they're looking for salium or
Nope.
salium.
Careful.
Calcium?
It's 2 past argon, right?
Yeah. It's
Calcium.
Calcium.
calcium. I'm so I just
Yeah.
I had my mom woke me up. She's like, "Hey, buddy, it's
Don't
10
worry.
o'clock.
Don't worry.
We're in class."
I've been in a daze, many days, so don't worry. Okay.
I fell asleep at like 8 yesterday, and I woke up at 12. I've had like no sleep.
Yeah.
Y'all want to know something wild that's gonna make you worry?
What?
I've started exercising.
Oh, geez, Arthur.
I'm gonna reassure you I haven't.
Oh, geez.
It's like,
Okay.
Yeah.
Part B. It says calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of an atom. Okay. And the valence shell would be this one. How do I know that that's the valence shell?
it's the last one.
Yep, it's
It
the
takes
last.
least
It's the one
energy.
farthest away. So remember, the ones farthest away from the nucleus are the valence electrons. Okay, they're usually s and p electrons. Okay, they're s and p electrons that are on the outside. So there's the valence shell. It says calculate the wavelength in meters. Now we don't have the form. I didn't copy the formula sheet into here, but here's the equations. We did this way back probably in October. Okay, so this is Planck's constant. It's given on the worksheet. Okay, and then this is the frequency. But you guys will notice, and then this is the energy. Okay, so you'll notice we don't have anything about frequency. Okay, but we do have something about energy, and it's asking about wavelength. So there's no wavelength in that equation, but there's another equation. Oh geez, why can't I scroll? There we go.
What is the equation with mu?
What one?
With mu?
Well, so this one is new. Like I think it said new. This one, it's weird. Viscosity, or that one that looks like a little lowercase m, is mu. Okay, so and it turns out that this one, frequency, is equal to, this is also on the worksheet, speed over wavelength. So I know this would be a stretch. This would be one I think that a lot of people miss because we don't really review it. This is more physics. But if this is new and I substitute that in there, I get the formula E equals hc over nu. And they're asking you to find the wavelength. Okay. So if I'm solving for wavelength, I need to do a little switcheroo. Wavelength would equal hc over let's see, energy, right? If you do some algebra and move things around.
Mm-hmm.
So this is just now plugging things in, and I have them here because I always forget them. I kind of remember the numbers. I forget the exponent. 6.626 times 10 to the negative 34 times, you guys remember how fast light travels?
Isn't it
3 something.
It's 300. It's 300 million.
Hey.
And then you guys remember the units that go with it?
Meters per second.
Meters per second. Okay, so 300 million meters per second, or three times 10 to the 8th. Again, this is given. So don't worry. And I doubt that this question again would be on there. I'm not going to say it's not on there, but it's probably less likely. And then energy, you're going to go up to your plot. You're going to plug in the energy that's given for the valence shell. So 0.98 times 10 to the negative 18. 0.98 times 10 to the negative 18. Okay, you're going to make sure you have a... Now, they're not going to prevent you from using Desmos, I don't think. But you're going to make sure that it's typed properly on whatever calculator. Oh, and then this was in joules. And you're going to cancel units, joules, seconds, and it comes out, because it's wavelength, it should be in meters, right? And it comes out to 2.03 times 10 to the negative 7th meters. So that electron, it's kind of crazy. The electrons that bounce off of things, they have a certain wavelength, and that wavelength, I think, would actually be visible to us. So because it's like that one's an ultraviolet. Turns out it's just beyond the purple light region. But this one, so you would need an ultraviolet detector to detect that energy. And that's the lowest energy electron. So the highest energy electron would probably be, you guys remember some types of electromagnetic radiation that's higher than or more energetic than ultraviolet?
Gamma?
Gamma, that's the highest. Probably these wouldn't be gamma because those are dangerous.
Oh, are they microwaves?
Microwaves are longer. They're less energy. There's one. They use them in hospitals.
Ultraviolet. I thought it went...
They use them in hospitals.
X-rays.
X-rays.
There
These ones probably you need an X-ray detector, and then this one needs an ultraviolet detector. Usually, the equipment that they use can detect all the way from X-rays up through visible, and they are very expensive. Okay.
Oh.
Okay. I know it's probably 10:30. I'm gonna try and let's at least look at the next question. We probably won't answer it. See if you can answer the first part, and then we'll finish the rest tomorrow. Let me switch to it. Where is my cursor? All right, here you go. Nitrogen dioxide, produced as a byproduct when you combust fossil fuels in an internal combustion, like a car engine. At elevated temperatures, it decomposes according to the equation below. The concentration of the sample is monitored as it decomposes, and it's recorded. So they measure how much NO2 is left, and they plot it versus time, and they have you look. They say identify, is this a first order, zeroth order, first order, or second order reaction? So when you get this, you're looking for what?
Which one's linear?
Which one's linear? So here you go. This one's linear. This one says 1 over the concentration of NO2 is linear. Is that zeroth, first, or second?
Second order.
Second
right?
order.
Because
Very good.
NO2
Yep. Zeroth will have just a constant. It looks like that versus time. And then first order is the natural log of a concentration. Okay.
I did initially say third order for a second one because you said it's 0.
I always forget 0 too, so don't worry. That's probably my fault. Okay, and then write the rate law. This is where we're going to stop for today. The rate of reaction would equal some constant times the concentration of NO2 to the second, and that is the definition of second order. Without knowing this data, you don't know that exponent. And do you guys remember what little k is called?
Constant.
It's called the rate constant.
Oh yeah, sorry.
Yep. And just quick and I'm stopping after this. This would be molar rate is always in molar per second. And this is in, right here, this is in molar squared. Okay, so the rate constant in this case would have the units of molar seconds, 1 over molar seconds on bottom. So molar seconds would be in the denominator so that it would cancel. When you multiply this times this, you end up getting a rate. So again, that rate constant, its units always change and it depends on the order. So okay. I'm gonna stop this. Do you guys have any questions while I get my recording finished up?